The DMSC framework has 4 components. Unlike the frameworks in other AI courses, DMSC is not a sequential process. It is not step 1, then step 2. All 4 components are active simultaneously in a well-operated AI system. There are 4 parallel responsibilities running continuously: de-deploy, the go-live domain, everything required to take a designed AI system from testing to production, configuration verification, real task testing, user training, documentation, handover, and the go-live checklist. Deploy has a specific moment the day the system goes live, but the quality of that moment is determined by everything that preceded it. Monitor, the ongoing observation domain. Monitor answers one question: is the system performing as expected right now? Not in testing, not last month. Right now, with real users, on real tasks. Monitoring covers output quality checks, usage tracking, failure detection, and the intervention triggers that convert observation into action. A system without monitoring is a system that degrades silently. Scale, the expansion domain. Scale addresses what changes and what must not change when a working system is extended to more users, new use cases, or new teams. Scaling without a structured approach breaks systems that work perfectly at small scale. Section 4 covers the 3 tests that determine whether a system is ready to scale. Control, the governance domain. Control defines who has authority over the system, how changes are approved, what risks are managed, and what happens when the system needs to be updated, restricted, or retired. Control is the only DMSA component that never has a natural endpoint. It is permanent. 4 components, all running simultaneously, all required. Before going into each DMSA component in detail, I want you to complete one exercise: an audit of the AI systems you are currently responsible for. 4 questions. For each AI system you use or manage. Question 1. Who is the named operator responsible for this system right now? Not a team, not a department. A specific person who would answer a call at 9 a.m. if the system was producing poor outputs. If you cannot name one person, the system has no operator. Question 2. When was the last time anyone checked whether the system's outputs were still accurate and useful? A structured review where someone looked at real outputs and assessed their quality. If the answer is never, the system has no monitoring. Question 3. What happens when the system produces a significantly wrong answer? Is there a protocol? Does anyone know how to report a problem? If the answer is we deal with it as it comes up, the system has no failure handling. Question 4. Has anyone updated the system since it was first deployed? Has the system prompt been reviewed? Have the knowledge documents been checked for accuracy? If the answer is not really, the system has experienced drift without anyone noticing. Complete this audit now. Pause the video. Walk through it for one AI system you manage. Write down the answers or be honest about the fact that you do not have them. This audit identifies which DMSC components to prioritize. The rest of this course gives you everything you need to close every gap it reveals. I want to start this section with a distinction that changes how you think about AI deployment. Most AI systems are not deployed, they are made accessible. There is a significant difference between those two things. A system that is accessible exists and can be used. You have created a Claude project or a custom GPT, you shared the link, people know it exists. That is accessibility. A system that is deployed has been configured correctly for its production environment, tested with a full range of real inputs, communicated to its users with clear and specific instructions, documented so people know how to use it well, and handed over to a named operator who is responsible for it. That is deployment. The gap between accessible and deployed is where most AI systems fail. Not because the technology does not work, because the conditions for the technology to work reliably were never established. A concrete example: a team deploys a customer service response drafting system. They spend 3 days configuring the system prompt and testing with ideal input. They send one email to the team. The AI drafting tool is live. Here is the link. 3 weeks later, half the team tried it once and then stopped using it. The other half is using it, but the outputs require significant editing before they are usable. What went wrong? The system was accessible. It was never deployed. There was no training on how to submit a good input, no documentation explaining what to do when the output was not useful, no named operator to improve the system based on what users were experiencing, no monitoring to detect that the edit rate was high. The technology worked, the operation did not. In the next lecture, I cover the 6 components that transform accessibility into deployment. 6 components. Every professional AI deployment requires all 6. Component 1, configuration. The system is set up correctly for its production environment. Knowledge documents are current and accurate, not a first draft that nobody has reviewed since setup. The system prompt reflects the actual tasks real users will submit. Access settings are correct, all verified before go live. Component 2, testing with real tasks. Not testing with ideal inputs, testing with the full range of inputs real users will actually submit, including partial information, ambiguous requests, edge cases, and inputs outside the system's intended scope. A system that only passes ideal tests is not ready for deployment. Component 3, user training. A clear, specific statement of 3 things: what the system does, how to submit a good input, and what to do when the output is not useful. This is the 3-point training summary. 15 minutes to design prevents the most common adoption failures. Component 4, communication. Users know the system exists, what it is for, and where to find it. Specific enough that someone can start using it immediately after reading. Not a general announcement, a practical introduction that tells users exactly what to do on day one. Component 5, documentation. A single reference document that answers: what does this system do? How do I use it? What do I do when it produces a poor output? Who do I contact? One page is enough. Component 6, operator assignment. A named person is responsible for this system, not a team, a person. Their name is in the documentation. They have committed to the monitoring practice. They have the authority to update the system when needed. All 6, not 5, not 4, 6. The go live checklist is completed immediately before the system goes live. 8 items. All 8 must be checked before the system is announced to users. Item 1. Knowledge documents are current verified within the last 48 hours. Item 2. System tested with 10 real-world inputs, acceptable output on at least 8 of 10. The test must include incomplete inputs, ambiguous requests, and at least one out-of-scope input. Item 3, access configured correctly. The right people have access and nobody else does. Item 4, user training material prepared and distributed. The 3-point training summary sent to all users before go live. Item 5, system documentation published and accessible. Item 6, named operator confirmed and briefed. They know they are the operator. They know what monitoring they are responsible for. Item 7, first monitoring review scheduled within 7 days of go live. A specific date and a specific person. Item 8, failure reporting route confirmed. Users know how to report a problem. The operator knows they will receive those reports. If any item is not checked, the system is not ready for go live. Deploying with open checklist items creates problems that are predictable, preventable, and significantly harder to fix after deployment than before. Two of the six deployment components, training and documentation, are most commonly underinvested, and they are the ones with the most direct impact on whether people use the system after go live. The 3 point training summary has three elements. First, what the system does specifically. Not this system helps with research tasks. Yes, submit a topic, a context description, and the audience for the brief. And this system produces a structured 2 page intelligence brief in under 2 minutes. Specificity tells someone exactly what task to try it on. Second, how to submit a good input. This is the highest value training element. Most AI system failures trace back to poor input. Show users the specific input format that produces the best output. If there is a template, give it to them. The 15 minutes you spend designing this template saves your users hours of frustration. Third, what to do when the output is not useful. This is the element most operators skip and the one that determines whether someone becomes a regular user or reverts to their old process after one bad experience. Give a specific next step. Revise your input with more context. Report it to the operator using this link. Contact this person if you are unsure. Documentation follows the same logic. 1 page, 4 headings, what this system does, how to use it, what to do when the output is poor, who to contact, short enough that people actually read it. I will walk through a complete deployment using a real professional example. A customer service response drafting system for a team of 8, handling 150 inbound inquiries per week. Configuration: 4 knowledge documents, a product FAQ, a list of known issues and resolutions, a tone guide specifying formal, empathetic, and specific as the 3 required voice characteristics, and an escalation matrix listing which inquiry types require a human response. Each document reviewed on the day of deployment to confirm it is current. Testing: 20 inquiry types from the previous month's actual inbox. Includes 3 complaint messages, 5 complex technical inquiries, 4 requests for information not in the knowledge documents, and 3 messages with unusual formatting or incomplete information. 17 of 20 produce usable drafts. 3 reveal knowledge document gaps that are resolved before go live. Training: the 3 point summary emailed 48 hours before launch. The system produces a draft response you review, personalize, and send. Submit the full customer message plus any relevant account history. If the draft is significantly wrong, report it to the operator using the link in the documentation. Communication: 1 clear announcement email with training summary and documentation attached. Documentation: 1 page in the shared drive. 4 headings. Operator. The team lead is named operator. First, monitoring review scheduled for the following Friday, 7 days after go live. That is a complete deployment. 6 components, 7 days of preparation. The difference between a system that works and one that does not. Monitoring is not checking that the system is still running. That is availability monitoring. AI operations monitoring is checking that the system is still producing useful, accurate, appropriate outputs for the real tasks it is being used for right now with real users. AI systems degrade in production in ways that are not obvious from the outside. Knowledge documents become outdated. The range of inputs users submit evolves beyond what was tested. New edge cases accumulate. The tasks the system is used for drift from the original design. The system continues to produce outputs, plausible looking, confident outputs that are increasingly misaligned with what users actually need. None of this is visible unless someone is looking. In most organizations, The system was deployed perhaps well and then left to run. Nobody looked at the outputs. Nobody tracked whether people were using it. Nobody updated the knowledge documents when conditions changed. The system drifted silently until a failure became too visible to ignore. Monitoring prevents this through consistency, not complexity. A monitoring practice has three elements: quality checks, usage tracking, and intervention triggers. Quality checks tell you what is happening. Usage tracking tells you who is experiencing it. Intervention triggers tell you when to act rather than continue observing. All three are required. In the next four lectures, I cover each one in detail. Quality checks are structured reviews of system outputs, not reading every output sampling. 10 outputs per week, 15 to 20 minutes, reveals patterns that no other method catches. Three quality dimensions for every sample review. Accuracy. Does the output contain information that is factually incorrect or not supported by the knowledge documents? One confirmed hallucination in a sample is a signal. Two is a serious signal. Three is an intervention trigger. Something must change before the next review. Accuracy is the first dimension because it has the highest consequence in most professional AI systems. A customer service response with incorrect product information, a research brief with an unverified claim, a performance report with a metric that does not match the source data. Relevance. Does the output address the actual task submitted? A system that produces technically accurate but tangentially relevant outputs is failing its users, even if every statement is correct. Relevance degradation usually signals that inputs are drifting from the system's design. Format consistency. Does the output match the format the system was designed to produce? Format drift indicates that the system prompt needs attention. It often accompanies other quality issues and is a useful early warning signal. The sample review process is 5 steps. Select 10 outputs at random from the most recent week. For each output, assess against the 3 dimensions. Score each as no issues, minor issue, or significant issue. Count significant issues and check against intervention triggers. Record results in the monitoring log, 15 to 20 minutes every week. Done. Usage tracking answers a different question to quality checks. Quality checks tell you how well the system is performing. Usage tracking tells you whether people are using it and using it in the way it was designed for. This distinction matters because adoption collapse and quality degradation are different problems with different causes and different solutions. You cannot tell the difference without tracking both. 3 usage metrics cover most AI systems in professional environments. Weekly submission count. How many tasks were submitted this week? A sharp drop is a signal something has changed in either the system or user behavior. Track weekly. Note significant changes. Output use rate. What proportion of outputs were actually used, sent, submitted, published, or otherwise acted on? If outputs are being discarded at a high rate, users have found the system unreliable. More informative than submission count alone because it captures whether the system is delivering value, edit rates. For systems that produce drafts, what proportion are used without significant editing, with light editing, or with significant rewriting? A rising significant rewrite rate is the most valuable leading indicator of quality degradation. It rises several weeks before users stop submitting altogether, giving the operator time to address the root cause before adoption collapses. You do not need a technical dashboard. A shared Google Sheet updated weekly by the operator is sufficient. Intervention triggers convert monitoring observations into operational responses. Without triggers, monitoring is observation for its own sake. With triggers, monitoring produces decisions. The most important thing I can tell you about intervention triggers, they must be specific. Not specific in the sense of being detailed, specific in the sense of being precise enough to produce a consistent decision when the threshold is reached. Weak trigger. If quality seems to be declining, review the system. This cannot produce a consistent decision because seems to be declining means different things to different people. It also has no response review. The system is a general intention, not an action. Strong trigger. If more than 2 of 10 sampled outputs in any week contain information that cannot be traced to the knowledge documents, the operator reviews the knowledge documents and system prompt within 48 hours. 4 elements: threshold, more than 2 of 10, detection method, sample review, response review, knowledge documents, and system prompts, time frame 48 hours. Every intervention trigger must have all 4 elements. Without any one of them, a trigger does not produce consistent action. How many triggers? Between 3 and 7. Fewer than 3 and you will miss important signals. More than 7 and the monitoring practice becomes too complex to sustain. A trigger that is never reached means the system is performing well. A trigger that is frequently reached but produces no response means the trigger is wrong or the response is not being executed. The monitoring log records every quality review, every usage observation, every trigger event, and every intervention for an AI system. 5 columns: date, what was checked, what was observed, whether a trigger was reached, what action was taken, 1 row per review, updated weekly by the operator, stored where the system owner can access it, 2 distinct purposes. Short term, the monitoring log drives the intervention cycle. Observe, assess against triggers, act or continue. The log creates the discipline of completing the cycle. If the log has not been updated this week, the review has not been done. Long term, the monitoring log is the evidence base for control decisions. When the system owner asks, how has this system been performing? The monitoring log is the answer. When a governance review asks whether the system is still fit for purpose, the monitoring log is the evidence. A system without a monitoring log is a system that an operator cannot account for. In professional environments where AI systems make recommendations, produce reports, or draft communications that affect real decisions, being unable to demonstrate operational oversight is a governance failure. In the next lecture, I show you how to build and maintain a monitoring log in a 15-minute setup. 3 consistent, predictable reasons why AI systems that work at small scale fail when extended to more users. Reason 1, context dependency. Original users develop an intuition about the system. Over time, they learn what kinds of inputs produce good outputs, the system's edge cases, how to interpret imperfect outputs. New users have none of this calibration. They submit inputs the system was not designed for and interpret outputs without the experience to spot when something is off. This is not a failure of new users. It is a design failure. Reason 2, knowledge document mismatch. Knowledge documents were written for the original context, the original team's products, processes, terminology, and concerns. When the system scales to a new team with different products and different processes, the knowledge documents become increasingly inaccurate and irrelevant. The system continues to produce confident outputs. They are just not right for the new users. Reason 3, governance dilution. When one person operated the system, they made all the judgment calls. When 20 people use it, those calls happen without the operator's knowledge. The system is being used in ways it was never designed for, and nobody has made a deliberate decision about whether those uses are appropriate. All 3 failure modes are predictable. All 3 are preventable. Before scaling any AI system, 3 readiness tests must all pass. If any one fails, the system is not ready to scale, regardless of how well it is performing for current users. Test 1. Quality at current scale is stable. The system is producing consistent, acceptable output. The monitoring log shows a stable quality trend over the last 3 to 4 weeks. The edit rate is within acceptable range. The submission count is stable. If quality is inconsistent at small scale, scaling multiplies the inconsistency. Test 2. The knowledge documents accurately reflect the new user's context. This requires the operator to actively review documents from the perspective of the new user group, their products, processes, terminology, concerns. This test almost always requires knowledge document updates before scaling. Test 3. The operator can sustain the monitoring load at the new scale. Monitoring 20 users requires more time than monitoring 5. Before scaling, confirm the monitoring practice is sustainable at a new scale or that monitoring will be shared or delegated. 3 tests. All 3 must pass. Document the results before proceeding. If any fails, document what needs to change first. When an AI system scales, some elements must change and some must not. Confusing these two categories is how well-intentioned scaling events break working systems. What must change? The knowledge documents almost always required. Review from the new user's perspective and update for their context. Products, processes, terminology, specific concerns. Update before the new users are given access. The user training material. The 3-point summary should reflect the new audience. Their most common tasks may differ from the original users. Examples should come from their work, not the original teams. The monitoring practice. As the user base grows, sample size or review frequency should increase proportionally. The operator's briefing. The operator needs to understand the new user's context well enough to assess quality from their perspective. What must not change? The system's core purpose. The fundamental design, what the system is for and what it is not for. Changing scope to accommodate new users without governance approval is how systems drift from their intended purpose. The intervention trigger thresholds. These were set based on what is acceptable for this system. They should not be relaxed simply because scaling creates more outputs. The control authority structure. Who has authority to change the system? And what changes require what level of approval? Knowledge documents are the most important thing to update before scaling. They are the primary mechanism through which the AI system understands the context of the tasks being submitted. When they are accurate and relevant, outputs are high quality. When they are calibrated for a different group, outputs miss the mark for new users. 4 steps. Step 1, identify the gaps. Review each document with the new user group's context in mind. What information do new users need that is not currently present? What information is inaccurate from their perspective? Step 2, update for accuracy. Any factual information that does not accurately reflect the new user's environment needs updating. Products, processes, contacts, terminology, pricing. Step 3, add new context. New users may have concerns, use cases, or requirements that original users did not add entries that address these specifically. Step 4, test with new user scenarios. Before go live for the new group, run 10 inputs typical of what they will submit. If outputs are not consistently high quality, identify which knowledge document gaps are responsible and address them. This preparation takes time, significantly less time than recovering from a scaling event that produced poor outputs and eroded confidence before the system had a chance to demonstrate its value. A complete scaling event. The customer service AI system extending from a team of 8 to a second team of 12 in a different product division. Readiness test 1, quality stable. The monitoring log shows a stable edit rate of approximately 15% for 6 weeks. Submission count stable at 150 per week. 2 trigger events occurred, both resolved within 48 hours. Test 1 passes. Readiness test 2. Knowledge documents for the new team. The operator reviews documents with the new team's product range in mind. The FAQ covers only the original product. The issue resolution list references processes specific to the original division. 3 or 4 documents require updates. 4 hours of updating. Test 2 passes. Readiness test 3. Monitoring load. The new team adds 80 submissions per week. The operator assesses whether reviewing 15 outputs per week is sustainable. It is. Test 3 passes. The scale event. Knowledge documents updated and tested with 10 inputs from the new team's inquiry types. Training summary adapted for the new team's most common inquiries. New team briefed using the updated training summary. First monitoring review for the combined system scheduled for 5 days after go live earlier than standard to catch any immediate issues. That is a structured scaling event. 3 tests, 4 hours of preparation, an adapted training summary, and an early monitoring review. Every other DMSA component has a natural phase or rhythm. Deploy has a go-live moment. Monitor has a weekly cycle. Scale has specific expansion events. Control has no endpoint. Control is the continuous commitment to keeping an AI system aligned with the organization's actual needs, actual risks, and actual standards. Those things change, regulations change, team structures change, tasks evolve, new risks emerge, personnel change, people who understood the original design leave, and replacements have different assumptions about what the system is for. A system without active control drifts. It continues to run, producing outputs that look similar to deployment, but the context has shifted and the system has not shifted with it. Outputs gradually become less aligned with what users need, less compliant with current standards, less appropriate for the organization's current risk tolerance. The most insidious characteristic of drift is its invisibility. The system produces a confident output that is wrong. A compliance concern is identified. A new team member asks why the system handles something in an outdated way. These moments reveal drift that has been accumulating quietly for months. Control prevents this through 4 specific responsibilities. Named ownership, a specific person accountable for the system. Change approval, a defined process governing how changes are made. Risk management, a documented understanding of what risks the system poses. Retirement, defined conditions under which the system will be taken offline or replaced. 4. Responsibilities. All 4 must be active for the entire life of the system. The first control responsibility is named ownership. The most important word, named. Not a team, not a department. A specific person, identified by name, accountable for the system's behavior and its outcomes. Why one person? Because accountability that is shared is accountability that does not exist in practice. When something goes wrong with a system owned by the technology team, the question of who is responsible has no clear answer. Nobody leads the response. Nobody owns the communication with affected users. Nobody decides whether to take the system offline during investigation. Named ownership resolves this. If someone asks, who is responsible for this system, there is an answer. If the system produces a harmful output, there is someone who leads the response. The named owner has 4 responsibilities. First, final authority. on what the system does and does not do. Second, they approve significant changes before those changes go live. Third, they are the point of escalation when the operator encounters a situation the monitoring practice cannot resolve. Fourth, they are accountable to the organization's leadership for the system's performance and compliance. The named owner and the operator are not always the same person. The operator may be a team member, the owner may be a senior stakeholder. Both roles are required, but the owner must be named, briefed, and genuinely accountable. If you cannot name the owner of an AI system you are responsible for, naming one is the most important action to take after this course. Not all changes to an AI system carry the same risk. Treating all changes the same creates either excessive bureaucracy or excessive casualness. Change categories resolve this. 3 levels: minor changes, low risk, correcting errors without altering system behavior, updating a factual error in a knowledge document, fixing a formatting issue in the system prompt. These can be made by the operator without additional review, provided they are logged in the monitoring record. Moderate changes, medium risk. Changes that may affect output quality or the range of inputs the system handles. Updating tone guidelines, revising the system prompt to handle a new type of request. These require a second person's review before going live, ideally, the named owner or a peer with relevant expertise, and a test run to confirm the change produces the expected improvement. Significant changes, high risk. Changes that alter the system's scope, its authority, or its handling of sensitive information, extending to handle a new category of tasks, changing how the system responds to compliance-relevant requests, adding or removing users with elevated access. These require the named owner's explicit sign-off and a full test run before going live. Also documented in the operational record with a rationale, 3 categories, 3 approval requirements. Define them for each system before that system goes live. 3 risk categories are relevant to almost every AI deployment in a professional environment. Risk 1, hallucination risk. The system produces plausible sounding but factually incorrect outputs, and users act on those outputs without independent verification. This is the primary risk for systems that produce information, research briefs, meeting summaries, status reports, customer responses, performance reviews. The consequence depends on context. A factual error in an internal draft is low consequence. In a client briefing or regulatory submission, it is high consequence. Mitigation. An accuracy instruction in the system, prompt specifying what to do when a claim cannot be verified. A monitoring check that tests outputs for unverified confident claims. Training that emphasizes the need to verify important factual claims before acting on them. Risk 2, scope risk. The system is used for tasks it was not designed for and produces unreliable, inappropriate, or misleading outputs in those areas. Mitigation, explicit scope boundaries in the system, prompts and documentation, and out of scope handling instruction. Monitoring that tracks input types and flags unexpected patterns. Risk 3, data risk. The system processes or retains information that should not be shared with the AI platform. Mitigation, guidance on what information should not be included in inputs or knowledge documents. Training, addressing data handling. Review of the AI platform's data retention policies before deployment. Document these 3 risks and any additional risks specific to your system in a risk register. For each risk, description, likelihood, potential impact, mitigation, and the monitoring check that would detect the risk materializing. AI systems have a life cycle: built, deployed, operated, and at some point retired, replaced, or fundamentally redesigned. The retirement decision is one of the most important governance decisions an AI operator makes, and the one most commonly avoided or made too late. Two types of retirement trigger. Both must be defined before the system goes live. Performance triggers. A performance trigger specifies conditions under which quality has degraded below an acceptable threshold and cannot be recovered through normal operations, knowledge document updates, system prompt revisions, monitoring adjustments. Example: if the significant rewrite rate remains above 40% for 4 consecutive weeks after 2 system prompt revisions and a full knowledge document review, the named owner initiates a retirement or redesign assessment. Specific: 40%, 4 weeks, 2 system prompt revisions, full knowledge document review. All conditions must be met. This prevents premature retirement from temporary issues, while providing a clear escalation point when issues are structural. Relevance triggers. A relevance trigger specifies conditions under which the system no longer addresses a genuine professional need, not because it is performing poorly, but because the need itself has changed. Example: if the professional process this system supports is significantly redesigned, replaced, or retired, the named owner initiates an assessment of whether the system remains appropriate within 30 days. The most common relevance triggers: a better solution becomes available. The organizational process the system supports is substantially changed. The team is restructured in ways that alter the nature of the tasks being submitted. Defining retirement triggers before deployment signals that AI systems are tools with a purpose, a life cycle, and an endpoint, not permanent infrastructure. I will walk through the complete deployment sequence for a real AI system, a research briefing system, following the actual steps you would take today. Step 1: configuration review. Open the system. Review each knowledge document. Is this information current as of today? And does it accurately reflect the tasks my users will be submitting? Update any gaps before continuing. Step 2: real task testing. 10 inputs representing the full range of what real users will submit. Include at least 2 incomplete inputs. Include 1 edge case. Include 1 out of scope input. Score each output: usable, needs minor editing, or needs significant revision. If more than 2 of 10 need significant revision, identify the root cause and address it before proceeding. Step 3: training material. Write the 3-point training summary for this specific system. First sentence: what the system does specifically. Second: how to submit a good input, including the format or templates. Third: what to do when the output is not useful. A specific action, not a general instruction. Step 4: documentation. 1 page, 4 headings. Step 5: go live checklist. Walk through all 8 items. If any item is not complete, do not go live. Document the open item and the date by which it will be resolved. Step 6: announce and monitor. Announce the system using the training summary. Schedule the first monitoring review for 7 days after go live. Run it. Record the results. 6 steps. If you follow this for every AI system you deploy, the most common go live failures will not happen to you. Deployment creates availability. Adoption is what people actually do with it. The gap between the two is where most AI system value is lost. 4 reasons adoption fails after a successful deployment. Reason 1: unclear value proposition. Users do not understand specifically what the system does well enough to identify tasks where it would help them. This system helps with research, is not specific enough. Submit a topic, context, and audience, and receive a structured 2-page brief in under 2 minutes. Give someone enough to decide whether to try it. Reason 2: first, Use friction. The first interaction is difficult enough because the user does not know exactly what to submit, that the output is poor. A poor first output produces the conclusion that the system is not useful. The first use guide addresses this. It tells new users exactly what to submit, in what format, to get a good first output. Reason 3. Non-use is invisible. Without tracking whether the system is being used, non-use is invisible. Invisible non-use is tolerated. Usage tracking makes adoption visible and creates a prompt to investigate and address the root cause. Reason 4. No evidence that it works. People adopt tools when they see evidence the tool produces value for tasks like theirs. The first few documented win-specific examples of what the system produced and what value it created are the most effective adoption driver. Collect them actively. 4 reasons, 4 interventions. All operational, not technical. AI systems fail in production. The question is whether you have designed what happens when they do 4 production failure modes in order of how quickly they manifest. Failure mode 1, quality degradation. Output quality declines gradually over weeks or months. Knowledge documents have become outdated. Inputs have evolved beyond what was tested. Tasks have drifted from the system's scope. This is the slowest failure mode and the most damaging. If undetected outputs continue to look plausible while accuracy declines. Detection, monitoring log, rising edit rate, or failing accuracy checks. Response, knowledge document review and system prompt update. Failure mode 2, scope creep in use. Users submit tasks the system was not designed for. The system produces confident but unreliable outputs for those task types. Detection, unexpected task types appearing in quality review samples. Response, user retraining on the scope boundary and consideration of whether scope should be formally extended. Failure mode 3, adoption collapse. Usage drops sharply. Users have found the system unhelpful and reverted to previous methods. Detection, submission count drop. Response, direct conversations with non-users to identify the friction points, followed by targeted training or system prompt revision. Failure mode 4, a high-stakes error. The system produces a significant inaccuracy and a user acts on it without verification. This is the highest consequence failure mode. Detection, user reporting. Response, immediate review. Direct communication with the affected user, knowledge document and system prompt correction, and assessment of whether other recent outputs may contain the same error. Design this protocol before it is needed. Your AI operation plans are organizational assets. An AI operations library makes them reusable and transferable. So the next time a similar system is deployed, the operator does not start from scratch. 3 criteria for including an operation plan in the library. First, the system addresses a repeating professional need, not a one-off task. Second, the DMSC operation plan is reusable across similar systems with minor adaptation. The go-live checklist, monitoring triggers, and control framework should transfer. Only knowledge documents require significant adaptation. Third, the system has been operated for at least 4 weeks, and the operation plan reflects real experience. An operation plan written before go-live is a plan. An operation plan updated after 4 weeks of monitoring is a record of what actually works. The operation card has 8 fields. System name, professional purpose, 1 sentence describing the problem and the user. DMSC summary, 1 sentence each for all 4 components. Tool platform, go live checklist. Intervention triggers with thresholds. Control framework owner, change categories. Retirement triggers, last operated and last updated. That final field is the most important for library value. An operation card without a date is not trustworthy for reuse. It may describe how the system worked 18 months ago. 4 steps for a complete scale event. Step 1. Run the 3 readiness tests. Document each result. If any fails, document what needs to change and a target resolution date. Step 2. Update the knowledge documents. Review every document from the new user group's perspective. Update for accuracy. Add new context specific to the new users. Test with 10 inputs from the new group before giving them access. Step 3. Adapt the training material. The 3-point summary should reference the new user's most common task, not the original users. If scaling to a significantly different audience, the training material may need substantial rewriting. Step 4. Update the monitoring practice. Review sample size, review frequency, and trigger thresholds in light of expected usage volume. Confirm the monitoring practice is sustainable. If not, identify who will share monitoring responsibilities before new users are given access. For large-scale deployments, dozens or hundreds of users, the governance questions become more significant. The named owner should be a leader with appropriate seniority. The change approval process should involve a formal governance body. The risk register should be reviewed by legal, compliance, or data protection professionals. DMSC applies at every scale, but the complexity of each component's implementation should match the scale and risk of the deployment.